All right, so this is your basic data, and of course, you wanted to satisfy the transversality. So you notice the sun, the long time ago, actually there is a constraint in the sense that this is located in module, and this means that when you apply lambda to your filtration, the filtration is not stable, but it is shifted at 0.51. Right, and the typical example that you have got in mind comes from geometry. Namely, suppose that we have a smooth morphism proper, let's say, projective family. Then you can take for your local system, you can just take you fix an integer I, and you can look at, for instance, this local system on the analytic manifold. So this means that you are already parameterizing homogeny with the I of the fibers. And each of the fiber is a smooth projective variety, so this homogeny group has a carrying-bond Hodge structure. And we're going to see the variation of that thing. Okay. So Philip also motivated by the Hodge conjecture introduced Hodge Locus. We try to study variational conjecture, introduce Hodge Locus. So here I will be a bit more general. I will really look at the collection of points. So it's just try to set a collection of points in the base such that the fiber of your variation of the structure has exceptional Hodge densities. By exceptional, I mean that what you can prove is that outside of the media set at the base, then basically all the fibers have the same Hodge densities, but then on some media sets you have more. And so when I say Hodge densities, I mean that I'm not considering only B, but really all the tensor power of B, and also all the tensor power of B dual. And then I'm looking at Hodge classes. So Hodge classes for me are always like 0, 0. Okay. So this is just defined as a subset of Sn. And not much was known about that till the end of the previous century. So then there was a fundamental result due to Cattani-Deligne-Kaplan. Was 95. That tells you that actually this locus is the countable union at Weil's spots. So I should notice here, of course, if you assume that the base is projective, this is an easy result because it's not hard, easy. It's not hard to see that it's a countable union of elements and varieties. And of course, if the base is projective by diagonal, you are done. But of course, this is not very interesting because this is usually transferred variation on projective basis. So quasi projective is much more interesting. So okay, so this is a countable union. It's not only media set, but it's actually a countable union of irreducible varieties of S. And let me give them a name. So of irreducible. And so those varieties that come back to the definition later are called expressions of varieties. Of S or B. Okay. So just as a remark, and of course, the motivation is that in the case where your variation of structure apart from geometry is predicted by the Hodge conjecture, because the Hodge conjecture tells you that each time you have an exceptional Hodge tensor, then you get actually an exceptional algebraic cycle in the fiber. Algebraic cycles have nice properties that can group together schemes. And so this gives you an algebraic family in the total space of project downstairs. So this would give you, but of course, the remarkable result is that you obtain this without the Hodge conjecture, and second, that this is true not only for variations of geometry, but actually for polarized variation of Hodge conjecture. All right, so now what I want to talk about is try to study more the geometry of this countable union of Weil varieties. And before doing that, we'll just go to the prediction of the field maps. So I remind you that actually you can describe a variation of structure by a transcendental map, which is for the PL map associated with the B. So let me denote it by phi. So this goes from the complex analytic manifold associated to the algebraic variety S, denoted by Sn, to some PL space, which I call a Hodge variety. So so what is this PL map? Well, you can think of it in two ways. One way of thinking about it, let me just mention it briefly. You go to the universal cover. So this is over S, and this is over some tilde. And then, because of the universal cover, all the systems are stabilized. You see that that thing is actually S tilde n, cos of pi, denoted by B. So actually, maybe it's better to really replace theoremorphic vector bundle. What this rather. It was my theoremorphic vector bundle. All right, so I get this kind of canonical civilization coming from that structure, and now I'm going to repose that here. Should do that. Let me erase this. Just keep the detail down. So the other side. Now here you have the Hodge equation on that bundle. And so when you put it back now, you can think of this just as being a family of filtrations on this filtration space. So basically, if you want to parameterize this, what you will do is just you will map S until to some flat manifold. And then the polarization tells you that actually you lie inside some open subset of that thing. So that's one way of seeing it, but actually you can make things, and then because of the existence of monodromy, the thing will just go to a quotient where gamma is essentially some set of equal points. So this is one way of seeing the PL map. Actually, it can be a bit more precise. You have to remember that each time you have a Hodge structure, there is a canonical algebraic group, the Hodge structure, which is the non-portable group of the structure, which is essentially the fixator of all Hodge tensors in GLDQ for that Hodge structure. And so actually what you are parameterizing is at each point the non-portable group of that Hodge structure. So actually D is homogeneous under the real points of the geometric group. This is just backlighting. So, how do we see the Hodge Locus from the point of view of the PL map? Well, it's kind of easy. We are looking at exactly the set of points where the non-forte group becomes smaller, because there are some exceptional Hodge tensors. So this means that in this Hodge variety team of gamma, so I should emphasize that on this thing I absolutely no algebraic structure, just a complex manifold. If you are in week one, then usually this is what is called the schema variety and it is algebraic. This is basically the only case. Okay. So inside team of gamma, where you can parameterize all the guys of the form T prime of gamma prime corresponding to smaller non-portable, because this means that actually the non-portable group at that point is a group G prime corresponding also with Hodge Milton. And this is strictly found in GE. Now this is countable because those groups are defined with Q. Okay. So now when you PL map,
Sorry, I missed who is the prime.
Sorry?
I missed who is the prime.
So, inside this modular space, I'm passing as a possible Hodge.
It's a union.
Yeah, this is a union. This is a union of all defined tests. Here, the better. All right, and then the prime locus will be essentially just the preimage of this countable union by obtaining that. Now, if you look at that diagram, you see that this is kind of surprising because, well, we know that Hodge theory is essentially considerable, and this is related to the fact that this guy is not an equal quantity, and this feedback is not really quantity. It's purely one more thing. But nevertheless, when you take the preimage of those complex analytics at the level of gamma, then you get something at y. This is the content of Cattani-Deligne-Kaplan. So it tells you that basically each time you take phi minus 1 of this d prime of gamma pi, you get something at y. Okay. So now let me mention, because this is used in the proof, although I will not go into that recently with Ben Baker and Jacob Zimmerman, we try to understand how far phi is from the algebraic. And so we use the idea from communality to say that actually this dim gamma is a complex analytic manifold which has a nice same structure. It's a definable being the omnium structure R actually, so some kind of semi-algebraic structure. And that this map is definable in the omnium structure R and X. And so, and those submanifolds are submanifolds also definable in R and X. And then Cattani-Deligne-Kaplan's result is essentially a corollary of Petersen starting result, telling you that the complex analytic manifold, submanifold of an algebraic variety, which is also definable in omnium structure, that actually that's why. Okay. So what I would like to emphasize is that although all these results are very nice, it's usually very difficult to describe explicitly those loci. So what I want to do now is for people who are not so much used to that, give some comments.
So if I understood you saying the linearity gives you the finiteness?
No, the omnium analytic gives you the algebraicity of the finiteness one of each of these guys for essentially for free, once we this minimum. But of course, that is different in some omnium structure. But of course, not proving this, we essentially follow the same arguments as the proof of Cattani-Deligne-Kaplan. You have to study asymptotics of degeneration propagation of structure. We use a little bit less. We don't need the full multi-acyclic orbit theorem. We just need the estimates on the original. So it's a bit better from that point of view. So basically, just more able to market for us. Okay, but I don't want to talk about that. What I want to talk is really the geometry of this union. So, but let me give some examples of control sign. Well, of course, there is the example of zero, in case that everyone knows. So here, let's give geometric examples. So I will consider the universal curve. Here, my base will be y0 of 1. So this is the universal. Of course, I'm cheating the structure. Then what is the clear map? Well, the clear map goes from the identification of that thing. And this is just C, because as a modularized space, this guy is just A1 to well, here the group, the geometry of the group is SL2 for a Q, and then you just get the identification. Your team at gamma is actually just H, the upper space in your SL2. And here, everything is kind of very explicit, so this is where you can compute. If you have an empty curve point in that modularized space, then what you do is just associate class of H1 0 inside C squared, which is H1 of the curve with percussion in C. And actually, so H is inside P1. Right? So this point here, the polarization that actually lies here, and actually it's just a ratio of the periods of the standard unique one form or holomorphic one form multiplication on a given basis. Okay. All right, so the map in that situation is just mapping your elliptic curve. If you want, you can uniformize it as being C Z plus tau Z. You are just mapping it to the class of tau. And of course, in this particular case, in Marco, that this map is invisible. But this is very special to that situation. So the direction is just a J point. So now, of course, in this situation, actually the Hodge tensor that will appear will just be endomorphism. Say, and you just make a computation. So this is an order Q of tau. Tau is imaginary quadratic. And otherwise, this is Z generically. And so you see that actually the Hodge locus for the universal elliptic curves is just the union for all tau and H which are imaginary quadratic. Of the invariance J of tau. So there are a few remarks is that by classical result, this is actually a point in Q bar. So you understand Q bar and inside C, and of course this is that. So really here you see the countable union. So this example is easily generalized to higher dimension. So notice that this example is in weight 1, where I consider from degree 1. And similarly, you can look at the family of varieties. So take the universal principal polarized varieties of dimension G. And then here things become to be much more complicated if you want to describe explicitly this locus. You can do it purely in terms of group theory, but if you want to do it explicitly, this is kind of very painful. So, but let me indicate that there are pieces of arithmetic origins. For instance, you have the exact analogy as here, corresponding to those guys where elliptic curves have complex multiplication, that you can have invited with complex multiplication. But you have pieces also coming for geometry. So, for instance, the Locus, the varieties split as a product. Right. This tells you that there is an exceptional Hodge class in the endomorphism, some conjecture. Okay. And then again, while the classical theory of Shafarevich tells you that this thing is a countable union of special varieties defined by Q bar again, and that hence even for the usual topology in AG analytic. Okay. Yeah.
After points in Q bar on Locus, and that is an example.
Yes, many of them.
Yes. So what is the characterization?
So actually, the points which are the on Locus are exactly as you hear the characterization.
Yes, sir.
Well, there is not in true characterization, but what I'm saying is that actually those points they correspond to the point where tau is like and J of tau is also. It's one way of saying it. Both are put together.
Okay, yeah.
It's by the same thing here. Okay, so this is still in level 1. So let's go to a more interesting example from the point of view of geometers, where so again it should be noticed that in this case the PL map is just the identification of AG with a Shimon variety, and the PL map is algebraic. This is very special to weight 1. So one interesting example is, let's take the universal family of hypersurfaces of degree T, smooth hypersurfaces of degree T, so universal degree T hypersurface in Pn plus 1 is also smooth. So of course, this family of hypersurfaces is parameterized by the projective space, that is the open part corresponding to smooth ones. You want to can quotient that you really get the moduli space, which is G of the right dimension, G of the right dimension. And of course, what we are looking at is the converging middle degrees. This is the only one which is interesting. So this is the local system. Okay, so let's start with maybe the simplest case, n is equal to 2. So now we are looking at surfaces in this. So XS is the surface in history. We are looking at H2 of that surface. So the interesting part is actually the Picard. And then there is a classical result of delta that tells you that for D at least 3, and the general XS, general surface is satisfied that the Picard is. Okay. Now, this tells you also that the Locus for this family, so you will be and look at this family, it will contain Locus that you hope to understand rather algebra, which is because the Noether-Lefschetz Locus, maybe this is a set of points S in the UTP, such that the Picard number is strictly larger than 1. Generic 1 has to be 1, but you just look at this Locus. This is not a full Hodge Locus, but at least it contains that one. And then there is a classical Noether-Lefschetz theorem that tells you that this guy, before Cattani-Deligne-Kaplan, they were able to prove that this guy is a countable union of the ones supply. Like this. This Noether-Lefschetz UPD is a countable union of varieties. And of course, people got interested in the density properties of this thing. And what happens is that actually this Noether-Lefschetz Locus itself, and so also the Hodge Locus, is dense in S, and there are two versions. Actually, this is also true for the analytic topology. So this was proven by Chiriberto, Harris, and Miranda for the Zaric topology. And then there is a classical argument to Green telling you that actually this is dense for the analytic topology. Now you can pass to the case n larger than 2. And okay.
You mean this is just an example, but there is more Hodge Locus.
Yeah, there are more Hodge loci, but in particular, this one is dense, and the full Hodge loci, which is will be dense. So I'm not trying to describe it as yes. Okay, so for n larger than 2, then there was basically no result before getting result. And not so clear what happened. So the goal of the talk is basically try to say something interesting about the geometry of this countable union. So let me state the theorem due to Baldi, Ullmo, and myself. That tells you that you have this situation. So you look at this family. As above, and then the result is that if n is at least 3, and d is at least 5, and nd is different from 4, 5, then actually this Hodge Locus. Okay, so we are not able to study the full Hodge Locus, but we can look at the Hodge Locus of positive dimension. This means that I'm considering these guys of the form phi minus 1 defined gamma phi, whose image under phi is not a single point. So an image in the field domain is of positive dimension. So if you think that your field map is immersive, basically, and basically you can that is just mean that the components are positive dimension. And the claim is that then this guy is algebraic. So this is not a countable union, but actually this is a finite union. So what I want to try to explain is what is the heuristic guiding this kind of results and how you get to it. And the heuristic comes really from the maps. It's something that you won't get if you think of the variation really as your local system and so forth. Because the field map the Hodge locus is really an intersection locus. So suppose that let me write it like this. If you want the Y is a special subvariety. So this means that if I look at my diagram, so my field map, then here I have some sub Hodge variety dy more gamma y, and here I have y, which is mapped to that thing. Okay, so now this is so y has to be an irreducible component of the image of that thing, right? But then it tells you that you should think of this really as an intersection theory problem. You are taking the image of S under the field map, and you intersect it with dy mod gamma y. So now with the intersection theory, the heuristic is that basically you have two cases. Either you have a typical intersection, or you have an atypical one, in the sense that the dimension is not expected. So I would say that the special subvariety is atypical if it does not have the right dimension. So basically, if phi of Sn and dy gamma y. So dy will be associated with the geometric property group of the restriction of my variation on y. Do not intersect geometry. So what it means is that if you look at the codimension of phi of y inside phi of Sn, it is strictly smaller than the dimension of dy mod gamma y in d mod gamma. When you use the intersection is transverse, it will be of the same dimension, but and otherwise I would say that this is typical. Okay, so this means that you can consider the Hodge locus as being really a union of special subvariety which are atypical, so the atypical Hodge locus and the typical one. Okay. Now, what are the conjectures? Well, which is the general spirit, the general heuristic for this kind of intersection problem is that this is what in the same is called the Zilbert-Pink conjecture of DHS. So Zilbert and Pink made this conjecture for Shimwa varieties, and then I made this conjecture for general variation of the structure, and then actually we have a stronger version in our paper with the Baldi and Ullmo. So it tells you that there are two parts of the conjecture. Is that if you look at the atypical locus, so this is atypical, so it should be rare. And this guy should always be algebraic. And the second conjecture is about the typical locus, and there are two things can occur. Either, well, the typical locus could be empty, and we have nothing to say, or it is dense, even for the analytic topology.
So this is not for geometric families, for any.
For any large function. As soon as you have a map, you can make this conjecture. Or is dense in S. So this is the main conjecture, and I hope that you will simple with map because this is actually kind of a network one. You believe that atypical stuff is rare and typical stuff is very common.
Sorry to interrupt, but how does this match with the previous theorem?
Okay, so I come to that now. So this is the conjecture. So now let's go to the results. So I will make a few assumptions in order to simplify stuff. I will assume that the joint four-plate group, so this is the reductive group, I can take, it's a joint group, this is a semi-simple group, and I will assume for simplicity that this is simple. Assume, so from now on, I will just assume that the joint imported group is simple. This will make the discussion easier, and this applies, for instance, in the case of coming to like those cases. And so G is equal, we can also reduce to the case where actually G is a joint and is equal to the algebraic member of the group. Yeah, so this is something that we want to discuss in too many details. Of course, you have the model of the system, you can take the algebraic member of the group, so you take the classic closure of the identity. And then there is a final result of believing that this group is actually normal in the derived group of G. And basically, the map sees only the new order. It does not care about the factor, so it does not cost too much to make this assumption. All right, so what are the results? So the first result I want to mention was analysis to proceed with our result with Baldi and Ullmo was a result with Dinowska, where we actually proved that the following thing was kind of surprising for me at the time, is that actually if you take the full Hodge locus of positive period dimension, so now maybe I should explain a little bit more. The idea is that it's much easier to touch the special varieties which are positive period dimension. There is some geometry to be done. If your special variety is just the period of one single point, then this would become basically an arithmetic problem, which then you will need other things. But what we prove is that in all situations, this guy is either algebraic or varieties. Yes. So you see that it was going into that direction, right? Except at the time was not we were not able to discriminate really between the atypical and the typical case, but at least we were able to prove that it was either algebraic, at least the positive part, or dense, but only for the last topology. So now there are three results in our paper with Baldi and Ullmo. The first one is that, well, concerning the first conjecture that the atypical locus is algebraic, what I can do is that I can consider the atypical locus of positive dimension. So I keep only the special varieties which are atypical, but also positive dimension, and then I prove under this assumption that the joint group, the joint group is simple, then we prove that this guy is algebraic. Okay. So basically, we are able to prove the first part, except that we cannot deal with spots. And not being able to deal with points explain why we need this assumption. Because if the group is not simple, then the PL domain is essentially the product. And then I have to ask that on each factor, when you are positive direction. Because otherwise I could get points on factor and then I don't know what to do. The theorem 2 is that concerns the second part of the conjecture is that there's a Hodge, a typical Hodge Locus is not empty, then actually the Hodge Locus is cancelled. So it is almost this statement, but certainly we still need those assumptions. And also we do not think that this guy is dense, but the full Hodge Locus is dense. And the problem could be that actually the atypical points are dense. This is what we can't exclude at that step. Okay, so this is the second theorem. And now, of course, when you see that you want a criteria,
You prove that it's algebraic, it's possible.
no, the atypical one.
Atypical.
So now I'm talking about the typical one.
I understand
If the typical one is not empty,
what is dense.
the full Hodge Locus,
Even non-positive.
even non-positive.
Okay, that's the point.
Yeah, this is the point.
Okay.
As I said, basically after our work, what remains to be done is really to understand atypical points. And here you see that appearing. That's the main point. Okay, and now what you want, you see that if you want a nice result about the Hodge Locus, you have to have a nice criteria telling you when the typical Hodge Locus is empty or not. And now I'll give you a criterion, which is very simple, is that if the level of V, so the level is the refinement of the weight, and come back to that. If the level of V is at least 3, it's more intrinsic than the weight. Right? If you start with a variation of Hodge structure of weight 1, then you can take a third positive power, then it will be of weight 3, but actually intimately it's still of weight 1. Then the Hodge Locus, the typical one, is empty. So this implies that the Hodge Locus of positive dimension will be the Hodge Locus of positive dimension, which is atypical, and so it will be algebraic. That's part. Okay, so let me come back now to the definition of the level. And this is not going to get there, it's really, because in some sense it's more nature than the weight. So the philosophy is that everything is taken care of by the Mumford table. So what time is it? No, it's still at home. So what is the level? Well, you take a generic point. So this means that the Mumford table at that point is the generic one. Now, what happens is that you can look at that point, then you can look at the algebra of that Mumford table, and because it is a representation of the Mumford table by the adjoint representation, it has a nature of Hodge structure. This means that when I complexify this guy, and of course it can be of weight 0 because this is inside the morphism by TS. So this guy will be composed as a direction for I equal to minus L of GI minus I, and it's really not stupid. I'm taking L as being the maximum index that this piece is non-zero. And this L is what I call the level. Okay. So I'm not looking at the weight, because the weight, as I said, if you start with weight 1, then if you subtract power, it will be a higher weight. But actually, the Mumford group will stay the same, and so this guy, so L is always smaller than the weight. So generally they will be equal, but in some cases be smaller. So typical example is the same family of K3 surfaces. If you look at the K3, you are looking at the convolution between 2, so it's equal to 2. But on the Lie algebra, because of the fact that H20 is 1, on the Lie algebra you get the weight 1 Hodge structure. This explains why the universe space is actually smaller. You don't have to. Of course, if you want to motivate that, you can go to Google Statistic, but you don't have to. If you like, I mean, if you like white books enough, that's fine. Okay, and another way of saying it, and now I want to explain why this is natural, is that if you look at the tangent space to the field domain at the point phi of S, then this thing is actually the sum for I is equal to 1 F of G minus I. And now, why does it have something to do with the atypicality? Well, the main point is this transversality. That tells you that the differential under the field now has to be counted actually in G minus 1. So really, what is absolutely crucial in all this business about atypicality is condition defined is transversality. Tells you that this field map is extremely constrained. It doesn't satisfy very rigid differential equation because this G minus 1 defines absolutely non-integrable distribution in the tangent number. So being tangent to it is very difficult. And so now you can imagine why the length of this equation has something to do with atypicality, because if you want things to be typical, you have that the tangent space have to add properly, such that you get the full tangent space. But with this condition, it is extremely difficult. It is more and more difficult as L becomes bigger and bigger. Okay? So, of course, in level 1, what happens is that this condition is empty. This is why you actually get an algebraic variety, a Schema variety. In level 2, well, we don't know exactly, things can happen, we have some results, but in level algebraic, what I'm saying is that in level algebraic, there are never any typical intersection. All the entire focus is atypical. And this is an easy exercise in thinking. So, so let me try to give some ideas of the proof. Are there questions about the results? So this result applied to the universal quantity of resistance. Sorry. Which one? Theorem 3 tells you that the typical part is empty, so that the full Hodge locus is atypical. Atypical, I don't know. French app and French probably. Okay. Is that clear? So if you think of the family, in the case of the family of the universal hypersurface of WD, the numerical condition that I gave you explicitly implies that the level of the variation that is string. So we can apply the result, and you get that in that case, the Hodge locus of positive dimension is completely atypical, and so it is algebraic as part of it. Okay. All right, so quick ideas of proof. I won't say much. So theorem 1, so the one about the fact that the atypical locus is algebraic, it's a consequence of functional transcendence result. So this is what is called the action for variations of our structure. So this is due to, so I conjecture it in the same paper in 2016, and then it was proven by Ben and Jacob. So maybe I will say sometime not write a precise statement, but you have to think that really what you are doing is that you are taking your algebraic variety S, you identify it, and you take the universal cover. Now, in some sense, you want to use a pure map to say that you put an algebraic structure on the universal cover. And the idea is that this guy goes to D, but this guy goes to a flag variety, which is an algebraic variety. So you have two algebraic varieties in the picture, that we check the S, and basically you want to compare those two algebraic structures. And the action with conjecture tells you that if you have an algebraic variety with a product, then actually, if it does not intersect generically the graph of the K map, then this is because you are counting in a locus. So there is a long history in the proof of this kind of thing, and other proofs that we recent by Ben and Jacob was using uniformity. But actually, what is nice is that since last summer, you don't need any at all. It's really a result about algebraic flat connections. Okay. So now you use basically this action result to prove the result in the following way. If some in the business, you show that using this action you show that the set of maximum. Yeah, maybe I should have made this one before. When I say that this locus is algebraic, remind you that this is a union of atypical special subvarieties of single dimension. I'm not saying that there are only finitely many. I'm saying that there are only finitely many maximum ones. There could be infinitely many, but there could contain infinitely many maximum ones. So what you really want to parameterize are the maximum ones and the set of maximum atypical components of your Hodge locus of positive K dimension is parameterized is at the same time definable in R and X. So you use thingness. So this is a definable set, and on the other hand, this is also a countable set. And the countability comes from the fact that the algebraic groups and the pictures are well defined as a Q. And so if you have a definable set which is countable, actually it is finite. So this is after this new proof of action by Pascal Cattani-Deligne-Kaplan this is the only part where we actually use definability, but in some sense this is also crucial. So I don't know how to keep this. About theorem 2, the typical locus. Well, in some sense,
this is definable in R exponential.
Yeah, R and X. This means that I allow the full real exponential function, and I allow any real relative function in restriction to a compact. Okay, I won't say much about theorem 2. Actually, theorem 2. We notice that there is an old result by Child saying that in Schema varieties, it's very easy to prove the density, and basically you just use density of regular orbits. That's basically it. And we notice that this argument works too as soon as you have a typical intersection. So this is how we get this density. So what I want to insist on is rather theorem 3, because this is a nice exercise on the BTOB. Right? What is it? So theorem 3 is essentially the theory. So what is the proposition? It's very easy once you know what you want to prove, but you just have to notice that it's true. So because that one still the assumption the group is adjoined and it goes to the algebraic group. So let's write the Hodge decomposition at one point, let me not write the point maybe. The Hodge generic point. And the first remark is that under this assumption, this group, this clear algebra is generated in level 1. This means that if you have a piece of algebra defined inside T, which is also a Hodge algebra, such that define the -1,1 part is equal to the -1,1 part for G, then actually the two algebra that would be formed. Okay, so that's the first exercise. And actually, this is the property of the Mondormi group. This is wrong in general for an unsorted group, but for the Mondormi group, this is fine. And two is that if, and this is where we use the level, if the level is at extreme, and if you have again a subalgebra, a subalgebra defined inside G, such that G minus 2 plus all the pieces minus n inside the complex equal to pi, then actually G is equal to G pi. And this is this piece that I had to notice. It's very easy. So what is the idea is that if all these pieces are contained in G pi, then you will be able to reconstruct G minus 1,1 by taking brackets. Because if this guy is contained in G pi, then also the conjugates G2, G2 minus 2, and so on. But then the brackets, if you have the at least level 3, you will, for instance, pair G minus 3, 3 with the G2 minus 2. And then we lie inside G minus 1, 1. Here in G pi minus 1, 1. And so actually, if you have those assumptions, you put this, and then you got it. So the idea is very simple. Let's think of a very simple case where you groups, something like that. So I'm in level 3. So this is the level 0 part. This is this block just above the diagonal with the -1 part. So you know that the differential of your PLMF will lie there. Then now you have the pieces. Yeah, zero, just distinguish. So this is n is equal to -2. And then you have this block, which is n minus 3. Now, if you have those 3 blocks, then you will have also the conjugate 1. And then by taking the bracket, you see that actually you will generate those ones. And then by the first part of them. So this is just an easy exercise in the theory. Okay, so now once you have this proposition, how do you finish the proof? Well, this is easy. So suppose we have y inside S special. So you have the Lie algebra of the joint comported group on Y, which is contained in the Lie algebra for S. And if Y is typical, you just see what it means. This means that if you look at the tangent space to the image of S plus the tangent space of the dy of gamma Y, this has to be the full tangent space of d of gamma. This is the typicality condition. But now you know that this thing is contained in G minus 1, 1. Okay. And of course, this one, you know that this is the direct sum of the Gy minus 1 minus II for I at least 1, and this one is the direct sum of the I less than 1 of the Gs minus II. So now you look at this, and you have to have this. But then this force is actually, this force is the sum of the G minus II for I at least 2 to be contained in GC, G prime. So then we can apply this. So you see that this is where this transversality plays a crucial role here. All right, so I still have 2 minutes. So I think this is kind of nice because now in some sense this transversality reduce this atypicality or typicality, and then understand better what happens. So, okay, for instance, if we have this family of universal hypothesis, we now know that this is an algebraic locus, at least for the positive dimension part. I have no idea how to describe this, but at least I know this is that part. So maybe I want to make a few more remarks. One more arithmetic aspect. Is that okay? The basic problem we can also suppose now that f is defined over some well, let's say for simplicity k inside C number field. Then, if you believe in the Hodge conjecture at the time, the Hodge conjecture predicts that the Hodge locus, the irreducible components of the Hodge locus should be defined over bar. Conjecture implies that special subparts are defined on bar. Then, what are the results in this direction? So, with Otnimaska and Urbanik, 21, we proved still under the same assumptions that G is simple. We proved that suppose that S is defined over K, then any Y inside S which is special of positive dimension. So the problem is still the same. We don't know what to do with the points. Positive period dimension and maximum for these properties. So the biggest component is defined over the bar. So we prove the expected thing, and moreover, the set of subprime is stable under the guard of the bar of K. That means that's what I did. And so, in particular, as a corollary of this result plus the part, then if the level is at least 3, and we are in this situation where we are defining the field, then the Hodge locus of positive period dimension is defined over bar, meaning that each of the varieties and stable under the bar. All right, so now today I was hesitating because I think many of you already heard that talk. I decided to give it again, but I could have specialized on the work of my student Tobias Kreutz. So we actually explain much better the results. Suppose now that you have f from x to s, not only defined over K, where K is finitely generated over Q. Okay. Then you have this Hodge locus. Of positive special positive dimension. Then you can define an analog. Not by looking at the variation of the structure, you can look at the least sheaf, the element sheaf for a topology. So let me call the corresponding locus as the L-Galois locus of S for P. Then the first thing he shows is that so this is the locus where the model representation has a smaller point. Then you can look at first he shows that this is the countable union of identity, and then he proves that actually the positive guy at the front side is that guy. So this is really in the direction of the Ullmo conjecture that the Ullmo group and the erratic Galois group are essentially the same up to taking tensors like Weil. And actually what we prove is that, well, we can take the absolute version of this. So we look at the absolute Hodge classes and prove that this is okay. And so in some sense, this explains better this result because it's clear for the atomic Galois group But for the absolute conjugate, let us see this has by the definition of what absolute conjugate is. So, but actually, the main argument is the same as here. It's a purely model argument. Okay, I think we'll stop here.